Studies and really lost 8 years of their
I
life.
feel like that wouldn't help.
What's up, Max?
How much? How you doing?
Good, you feel better?
I feel like studying too much would help. I feel like stressing too much about it would forget.
I don't know, I usually study once.
Usually I studied for 5 hours.
Yeah. Like
Existence
every day.
I'm tired of those.
I found 12 hours.
Because I don't think go home, get my daughter to go to work.
I understand. I found 12 hours.
I think that would make a good band name.
Baby.
Or is it Meatloaf Baby?
It's my
It's Baby Meatloaf. It sounds like Meatloaf made out of a baby.
Veal.
Deal.
My wife won't eat veal. Except for on a few rare occasions where she considers it delicious.
No, it doesn't. I don't.
Wait, it's not Coke Zero.
Dried up meatloaf.
It is.
Oh, but it's
I just poured it on top of my existing ice.
Oh, I see.
It's a little sneaky. A little sneaky. Okay, so we've got very exciting things to talk about today.
Including the fact that you're going to Tokyo.
Oh, you heard about that?
Yeah. What were you gonna tell us?
Speaking of a band name.
Today? Yeah, I've got a trip next week.
That sounds awesome.
Yeah, I'm kind of excited about it. I've never been to Japan before. So Professor Dent is going to come join us for the latter half of class today and make sure he's up to date on exactly where we are. And he's going to be with you next week. And he's fantastic. And he's my partner in the boot camp and the co-author of the book we're putting together. So he's going to be great. You're really going to enjoy that. And the goal for today is going to be to set up a little bit of kind of pre-calc to get the basic ideas. We're not going to be doing calculations yet, but we want today to understand what it is. Okay? By the end of the day today, we want to know what calculus is and kind of what it's good for. So in a nutshell, I'm going to describe this to you in terms of the relationships between position, velocity, and acceleration, which you are familiar with. We're also going to try to do this a little bit graphically, and one of the things we want to do from the very start here is build a very, very firm connection between our graphical intuition and our computational intuition. So position, as we've described from the beginning, is where the thing is at, and the variable we use for that in physics context is x. Now, velocity, on the other hand, is kind of where you're going. It's the way in which the position is changing, and we've laid the groundwork for that on several occasions. We've done kinematic equations and so on, and we've seen that that is something which can be written like this. And that d there, in your mind, if you're not used to seeing d's, you can think of them as deltas. But the difference is we're going to make the deltas very, very small. Kind of as small as we can make them in some sense. Infinitesimally small. And the difference between a d versus a delta is that if we have a delta, we're taking a longer interval for comparison. What we're really doing is something more like what's called an average velocity over the longer interval. So again, this would be the average v, whereas this we would refer to as the instantaneous velocity. And just right out of the gate here, I want to give you a little graphical intuition on that. So if we had a graph here, where the vertical axis was x as a function of t, of course, and the horizontal axis was t, and we imagined some curve like that, I want us to begin to real clearly get an intuition of what this is representing. Now, the first thing I want you to see is this. That's a little bit of t, right? The horizontal axis is the t-axis. That's a little bit of x, right? The vertical axis. So, delta x over delta t, which is, if we're talking about a graph, the vertical change over the horizontal change, that's what we call the slope. So the slope of this graph is related to the velocity, or more properly, the speed in this context. The science speed versus original velocity. Now, the thing I want you to get next is the distinction between that instantaneous and average velocity line. So in this interval between here and here, we went some distance forward, that's the change in x, while some time passed through. So if we just take a distance divided by a time, that's an average velocity. But the velocity along that curve was not necessarily constant, right? It was a little shallower here and a little steeper there. You see that? So, in fact, in this case, we were speeding up a little bit. So you should see that steep lines are fast. Steep lines are going lots of difference forward in a small amount of time, and shallow lines are slow. Ultimately, slow line, the horizontal line is speed 0. So steep lines are fast. Shallow lines are slow. And dx by dt is the slope at any one point x. And that's a little hard to define in some sense. It's the result of a limit. Because to define a slope, you have to have some distance. You have to have 2 points. Change in time and change in position. But as we bring those two things closer and closer and closer and closer, they ultimately converge to a point. And there is some slope that they're smoothly converging to. And that slope is very easy to understand intuitively. It's often what's called the tangent line to the curve. It's the line that just kind of kisses the curve on that one spot. So if we follow along, I think very graphically, you'll understand clearly, I think, what the slope is at each point. So as we move along, the point that I mean is the point that my fingers are connected in. But as I move that point along, the slope is constantly changing. Is that 100% visually clear? So at any one given point, we have a slope that's denoted like this. If we take the interval a little bit wider, then what we've got is actually an average slope over a continuum of points. In exactly the same way, we could be interested in changes in velocity. The velocity itself might be changing as time passes. And that's, of course, what we call the acceleration. Now, in most elementary applications, that's as far as we go. And if the forces are constant, F equals ma, then the accelerations are constant. And we start off with constant accelerations, and that was the scenario that we built our kinematic equations from. So we said, we've got to be careful not to apply these kinematic equations in places where they don't apply. Well, where do they apply? They apply in the cases where the acceleration was constant. One could, of course, imagine scenarios where the acceleration itself has a rate of change. And I think you know the word for that. That's we say that before? The rate of change of acceleration, do you know it?
Oh, yes, we did.
Yeah, we did.
Snap.
Not yet.
Ah,
Not yet.
crack. No, starts with
Sure.
snap.
Jerk. Jerk. Okay. Then the rate of change of jerk is
Snap.
snap.
Crack.
Yeah. It's hard to believe that's actually what they're called. The amount of time that one spends actually discussing those things and anything I've ever done is essentially zero. It's just sort of a funny little fact that you know in the back of your mind. Even when one is dealing with non-constant forces, one doesn't typically explicitly use the word jerk, even if one's dealing with a case where there is jerk. But suffice to say,
I have a question.
yeah,
In the case that jerk is changing,
Yeah.
what would the graph look like?
well, this would be one.
Wow.
This would be one.
Okay.
Yeah, because the acceleration in this graph is not constant.
Correct.
This was a negative acceleration. This was a positive acceleration, so that would be a graph with non-zero jerk. Any graph that represents a changing acceleration. So constant acceleration, we know what the graphs are. They're parabolas, right? So any position graph that's not a parabola has a jerk. Okay, so the three that we're going to be interested in, which I think if you understand this, you really understand the point of calculus in some sense, integral and differential calculus. The three that we're interested in are position, velocity, and acceleration, and they have this kind of canonical relationship to each other. This is the result of taking the slope of that. This is the result of taking the slope of that. So in English, we could say, if you have your Knack to English app, plug that in. This- yeah, it would say the English for that equation is velocity is the slope of the position versus time graph. And the English for this equation would be acceleration is the slope of the velocity versus time graph. In this process of going down, say if we knew the position and we wanted to find the velocity, that process is called differentiation, or taking a derivative. So taking the slope for example, moving from position to velocity, or from velocity to acceleration. So if you imagine a scenario where you know the position at all points, but you want to find the velocity, or you know the velocity at points, and then you want to find the at all times, all points, and you want to find the acceleration, that process, the process of taking a slope, is called differentiation, or taking a derivative. I took the derivative of something, means I got the slope of the corresponding graph. The slope of the corresponding graph is a new function. So given a position function, you can imagine taking the slope of that, and then you have a new function, which is a velocity function, or a position function. Likewise, if you had a position function, you took the slope of that, your new function is the acceleration. Now, we're going to do that graphically today, so that we make sure we understand the intuition. What Professor Dent is going to start with you next week. If we don't quite get to it today, we might crack it just a little bit today. Pre-calculus should take 1:45 minutes. What we're going to start to do, what we might crack today then, is to begin applying these ideas that we're going to look at first graphically in equation-based. So quantitatively, in addition to intuitive. One thing that this is never called is deriving. Please don't ever say that. I hear it an awful lot. People say, I derived such and such. Now, derived is a word, and it's used frequently in this context. Derived means I got this thing from that thing. It's like a process of a proof. I derived something. It's arrived at a conclusion based on some prior input. I proved this based on that. It is not the process of differentiation. Now, in the process of performing a derivation, i.e. deriving a result, one may often differentiate. But one must differentiate the meaning of those two words because they're not the same.
They're different.
They're different.
Oh,
Just
God.
know they're wrong.
I would like you to say that again, exactly the same.
We'll
Three
handle
times
it.
fast.
I think I love every second of it. The process of deriving a differentiation is
No, no. That's the point. We differentiate, we take derivatives. That's all we do. We differentiate and we take derivatives. Now, like every operation that we've encountered this semester, one needs to know how to do the operation and how to undo the operation. We take logs, we exponentiate. We take sine and cosine, we have arc sine and cosine, or inverse sine and cosine. Like all of those cases, we add, we need to subtract, we multiply, we need to divide. We have to do the inverse operation. The inverse operation is called integration. That's a very good name for it, for reasons which may not be immediately clear to you yet, but they will become clear very soon. To integrate means to bring all the pieces together. Add all the pieces together. That's what integrate means. Integration means bring all the pieces together. They will sometimes, in departments other than ours, teach you that this process is called anti-differentiation, or taking the antiderivative. That is in some sense formally true. It's the inverse process of taking a derivative, of performing a differentiation. We will never ever say that. We will say integrate, which is the right name for the thing.
What is chalk made of?
Just make it chalk.
I think that's the right answer.
Element number 2.
I only know two things. Helium.
Right.
It's got calcium.
Yeah, they'll say it's calcium. but that's-
Also, it's form or jello. They got
It's a research project.
Okay,
It's carbon.
There you go.
let's start off with a little graph here. So let's take some times here. Times in units of seconds. 0, 1, 2, 3, 4, 5 seconds. Let's also label each of these intervals so that we can refer to them. A, B, C, D, and E. And then corresponding, let's label positions up this way in units of meters. 1, 2, 3, 4.
2 months?
Did I do 2 ones? Oh goodness. Let's fix that right up. Thank you. So positions 1, 2, 3, and 4, and times 1, 2, 3. Okay, so let's imagine laid on top of this grid of positions and times, an object which is moving and whose motion is depicted in this graph. Once I've drawn that, what I want you guys to do is to think carefully if you can describe what's happening in each of those segments. So this is our graph. We know this relationship, which in English says velocity is the slope of the position versus time diagram. And then if we take larger steps, then we know that if you take larger finite steps denoted with the delta, interpret that as average velocity rather than instantaneous velocity. Okay, so what I want you to do is to look at each of those segments, A through E, and why don't you, in fact, put down A through E on your notes and stare at that picture for a minute and see if you can describe for me what the thing that's depicted in that graph is doing. Okay, so you can use words like this. Imagine that it's a car, for example. A car can be driving forward, it can be in reverse, it can have a foot on the gas, it can have a foot on the brakes, it can be coasting, it can be sitting still in park. So these are all things that a car can do. So use car-type descriptive words to see if you can outline what is happening in each of those 5 intervals of time. I'll give you a couple minutes.
Are we assuming that x is distance traveled?
So X is your coordinate location. It's where you're at on a number line. Okay. It's all one-dimensional motion. We're moving either forward and backward along a one-dimensional number line. And those are the coordinates of the number line, 0 and 4. Does everybody have an answer at least for A? Okay, let's check on that and see what we're doing. Now, before we do that, let's elaborate on this point a little bit. This is a one-dimensional number line. Okay, sometimes when people see this for the first time, they want it to be two-dimensional. We're just moving forward and backward. Okay? This is our road, and along that one-dimensional road, we can move forward and backward. But as time passes, okay, as time passes, we're doing that. Forward and backward over our road. Okay, segment A, tell me what you came up with. We're driving forward or backward? Forward. Do we have our foot on the gas, or the brakes, or are we coasting? Cruising. Cruising, that's exactly right. How can you tell that we're neither speeding up or slowing down?
It's a straight.
It's a straight line. The line is straight. Okay. What is the average velocity in segment A?
1 or 0. 2.
Okay, yeah. How far did we go forward?
2 meters.
We went 2 meters forward altogether. And how long did it take?
1 second.
1 second. Okay. So in this case, since the line is straight, the average velocity is also the same as the instantaneous velocity. So in segment A, what are we doing? We're moving forward.
2x per second.
Constant speed, yeah. 2 meters per second. And what's our acceleration?
0.
0. That's right. Neither speeding up or slowing down. Okay, everyone got that one? Perfect. What are we doing in B?
Slowing down.
That's right. We're slowing down. That's right. So at the very beginning of segment B, our slope is still 2, right? So 2 meters per second forward there. But by the time B is done, our speed is 0. Well, since that flat line is 0, we're neither moving forward or backward. Okay, so we're slowing down. So you'd say our foot's on the brakes, right? And is the car in forward or reverse though? So we're still going forward. What's our average velocity?
Still, it's 1.
Our average velocity is 1. Everyone see that? What's our acceleration?
Negative.
Is it negative? One agrees with that. What value is it? Can you tell what value it has?
1/2.
Let's assume that it's constant. That graph is reasonably consistent with the parabola segment, which would be a constant acceleration. It is negative.
-1.
What speed did we have when we started off?
2.
2. What speed did we end with?
1.
You sure?
Right there. Or
0.
0.
0, yeah. So the change in our velocity was what?
2.
Yeah, -2. So we went from 2 to 0. So the change in our velocity was -2. How long did it take?